A very good day, I bid to Dr. Royal and Dr. Hizami. My name is Jin Lin and would like to present to you about process design and optimization of integrated refinery and biorefinery. So to proceed my presentation today, I will first touch on a brief introduction which covers the project background, problem statement, objective and scope of study. Moving on next, I will present to you the literature review, followed by research methodology, results and discussion, and last but not least the conclusion and recommendation. Without further ado, let's proceed to the introduction. Here, I would like to give you an overview of my project. It is known that fossil fuels are fundamental input and driver to most of the economic activities. However, fossil fuels are non-renewable energy where its reserves are limited and are depleting. Burning of fossil fuel also brings impact to the environment as it emits greenhouse gases which leads to global warming. Hence here, I would like to introduce the usage of bio oil to replace the fossil fuels. However, high-quality fuels from bio oil requires costly upgrading process. Therefore, it is suggested that co-processing bio oil into existing refinery facility is able to reduce the processing cost, which is the main focus of this project. So how does this integrated system look like? Let's take a look on this diagram in which you have the gas oil from the conventional refinery system and bio oil from the biorefinery system, which then blended together with the gas oil and feed into the fluid catalytic cracking and hydroprocessing units in the refinery system. Next, here I have listed out two problem statements. Firstly, a systematic synthesis and design of the integrated processing facility is currently not in hand. Therefore, it is in need to design and optimize the integrated process to make it a feasible one. So the objective of this project are to develop the process correlations between feedstock and product use of FCC and HP units as function of bio oil to crude oil feed ratio and operational temperature. Next is to develop the process correlation as well, but it's between the feedstock and the utility duty. Moving on next is to compose the optimized structure and solve it using GAMS to obtain the most profitable feed and operational parameters. And finally is to carry out sensitivity analysis of different operational parameters on the profit. Now let's move on to the scope of study. Firstly, the biomass source is palm kernel shell PKS and empty fruit bunch EFB. The properties of the biomass are according to the one produced in Malaysia. Next, the types of bio oil are fast pyrolysis oil FPO and hydrodeoxygenated oil HDO. And finally, the refinery units involved in this project are fluid catalytic cracking unit FCC and hydroprocessing unit HP. Moving on next, I will present to you the summary of the literature review regarding the co-processing bio oil with petroleum oil. Study shows that bio oil is more prone to crack at elevated temperature as compared with conventional crude oil. This is due to bio oil has a higher amount of oxygenates present, as you can see in this table. Therefore, it's not desirable to feed bio oil into the CDU as a first step to avoid cracking. Hence, the literature found that co-processing of bio oil should be carried out in a residual cracking or upgrading units. Therefore, here I would like to show you the main technology used in co-processing. Firstly, we have the hydrotreating units, which is to remove the undesirable heteroatoms such as sulfur, nitrogen, oxygen. Moving on next, we have the hydrocracking units, which is to convert heavier fraction into a smaller ones and to remove heteroatoms. And finally, we have the fluid catalytic cracking, the FCC units, which is to crack the vacuum gas oil, the VGO, into smaller hydrocarbons to increase gasoline production and also promotes the oxygenation reaction. And as you can see from this table, the properties of the bio oil and petroleum are similar, and therefore the co-processing of bio oil with petroleum oil can be said to be a feasible process. Moving on next is the methodology of this project work. Before moving into details, I want to give you a rough idea about how the integration structure looks like. So here are the petroleum feed, the bio oil feed, and the processing units. And here is the block diagram of the integration structure. And as we can see, the integrated process begins where the bio oil is split into two strips and then mixed with the petroleum feedstock. And then the blended strips are then fed into the processing units to produce the desired product, namely the Naphtha, Distillate, and LCO. LCO is known as light cycle oil. And here I show to you the flowchart of my methodology, where the optimization work begins with the Aspen-HYSYS process modeling of the FCC reactor and the HP reactor. After that, surrogate model will be developed to correlate the process parameters, namely the operating temperature and bio oil to oil ratio with the feedstock product use and process heat duty. And with this, the optimization is then done in GAMS to search for the optimum process parameters that maximize the total profit, and finally the sensitivity analysis. Moving into detail, let's begin with the surrogate model development. Here I'm going to show you how I actually obtain the process correlations equation, which is important before composing the optimization model. So here we have surrogate model type 1, which is to correlate product yield with the operating condition, and surrogate model type 2 to correlate process heat duty with the operating conditions. And this is the general form of the surrogate model for this project, where E is the function of boil oil to oil ratio and operating temperature, and there are dependent and independent variables. The dependent variables are the product use and the process heat duty, whereas the independent variables are the boil oil to oil ratio and the operating temperature. However, to develop this surrogate model, we have to perform process modeling beforehand. For this process modeling, the XCC reactor and HP reactor are being modeled. So now let's understand the operating condition of the processing units. Here I show to you is the XCC operating conditions. The selected fluid package is Pan-Robinson since it is hypothetical and consists of light hydrocarbons. And here is the HP operating condition. The selected fluid package is also Pan-Robinson due to hypothetical and light hydrocarbons. And here is the feed specification. This is for petroleum feed. Moving on next, we have the FPO PKS feed specification. Here is for FPO EFP. And next, this is HDO PKS. And finally, here we have HDO EFP. So now I'm going into detail about how I actually developed my surrogate model. So firstly, data collection is done via the process modeling in Aspen HYSYS, where the simulation model was pre-developed and was re-simulated. So how is this simulation model being re-simulated? The answer is by varying the boil oil and petroleum fluid as shown in this table, and also the operating temperature as shown in this table. So by varying these parameters, the product used, which are Naphtha, Distillate, and LCO, are recorded. Also, the enthalpy is recorded, and the heat duty is calculated by using this formula. After that, data conditioning is carried out, where the basic data analysis is performed. Moving on next is the modeling, where I developed my model via the Microsoft Excel regression tool, and I analyzed my model by observing the Pearson R-square and adjusted R-square, and also remove the outliers. Eventually, I validate my model by observing the Pearson R-square and adjusted R-square value. Then I carry out the collinearity test, where the variance inflation factor, which is the VIF, is determined. And this is the final form of my model. And VIF can be calculated by using this equation, and the best condition is said to be less than 5. So with these process correlation equations, the optimization works can now begin. For the optimization in GAMS, I would like to first introduce the objective function, which is to maximize the total net profit of the integrated process. And as we can see from this equation, the total profit includes the product sales, raw material costs, and utility costs. Capital cost is not taken into consideration since the integrated process is performed in an existing refinery system as mentioned. Moving on next is the model constraints. Here we have the mass balance constraint, which govern the operations of the integrated process. Since the process used are a function of boil oil ratio and operating temperature, therefore variable constraint, which consists of boil oil to oil ratio and operating temperature as shown, are important. Next, the feedstock supply limitation also imposes additional constraint as shown, where the supply availability for boil oil is 30 m3 per hour and 150 m3 per hour for both VGO and LBGO. And finally is the non-negativity constraint to ensure that the feed flow rate and the operating parameters are not negative. And here is the cost constant used for this project. Finally is the sensitivity analysis, where I study the effect of boil oil to oil ratio, effects of operating temperature, and effect of market prices of products and raw material towards the total net profit. So here all the parameters are being varied for plus minus 5%. Without further ado, let us move into the first part of the results and discussion, which is the surrogate model development for the FCC unit. Now here is the process correlations for a naphtha yield from EFP boil oil. Firstly, we have FPO EFP. So after developing this surrogate model, here is the results, and this is the final form of the equations, which consists of two variables, namely the boil oil ratio R and temperature T. And it is determined that the R-square and adjusted R-square is close to unity, and the VIF is less than 5, which means that there is no redundancy in the selected variables. Moving on next is the HDO EFP, and this is the surrogate model results, and this is the final form of the equations. The R-square and adjusted R-square is also close to unity, and the VIF is also less than 5. Right now, why don't we do a little bit of process analysis based on these two equations? So firstly, you can see that our R has a positive variable. Whether it is valid? Yes, it is, because when the boil oil blend increases, more naphtha is produced due to synergistic effect that promotes higher catalytic cracking reaction. Next, the variable T is also positive because at higher temperature, the naphtha yield increases until a maximum of 545 degrees C as seen, where the naphtha yield starts to decrease due to overcracking. Moving on next, I present to you the process correlation of naphtha yield from the PKS barrel oil. Firstly, we have the FPO PKS, and after developing the surrogate model, here is the final result, and this is the final form of the equation, which also consists of variable R and T. The R squared and adjusted R squared is close to unity, and the VRF is less than 5. Next, we have HTO PKS, and this is the final result of the surrogate model development, and this is the final form of the equations. The R squared and adjusted R squared is also close to unity, and the VRF is also less than 5. As for the process analysis, based on these two equations, for the R for FPO PKS barrel oil, it has a negative coefficient, and this is valid as we can see that the naphtha yield is lower when the barrel oil blend increases. This is due to the lignin-derived monomers that is difficult to crack. However, the upgraded barrel oil from PKS results in higher naphtha yield, therefore H2O PKS has positive R. As for the temperature, it has positive coefficient, meaning that the naphtha yield increasing with the operating temperature until a maximum, as we can see from here. Moving on next, I present to you the process correlation of LCOU from the EFB barrel oil. Firstly, here we have the FPO EFB, and here is the result from the surrogate model development, and this is the final form of the equation, which consists of variable R and T. The R squared and the adjusted R squared is close to unity, and the VIF is less than 5. And next here is the HTO EFB, and this is a result from the surrogate model development, and this is the final form of the equation, which also consists of variable R and T. And the R squared and adjusted R squared is also close to unity, and the VIF is also less than 5. Now let's look at the process analysis for these two equations. For the R variable, it is negative and it is valid because higher barrel oil blend favors the naphtha yield. Next, the T has negative coefficients, meaning that the LCO yield decreases as the operating temperature increases. This is because at higher temperature, LCO tends to further crack into lighter products. Moving on next, here is the process correlation of LCOU from PKS barrel oil. Firstly, here is the FPO PKS barrel oil, and this is a result from the surrogate model development, and this is the final form of the equation, which consists of R and T variable, and the R squared and adjusted R squared is close to unity, and the VIF is also less than 5. From here is the HTO PKS, and this is the result from the surrogate model development, and this is the final form of the equation, which also consists of variable R and T. The R squared and adjusted R squared is also close to unity, and the VIF is also less than 5. Looking into the process analysis for these two equations, FPO PKS barrel oil has positive R coefficients, meaning that LCOU increases when the barrel oil blend increases because of the lignin-derived monomer, which results in the lower naphtha yield. On the other hand, R for the H2O PKS is negative, meaning that it produces high naphtha but lower LCO. For the temperature, it has negative coefficient because LCO tends to further crack into lighter products, reducing the LCO yields. So here we have the process correlation of the process heat duty from EFB barrel oil, and here is FPO EFB, and this is a result obtained from the surrogate model development, and this is the final form of the heat duty equations, which consists of R variable and T variable. The R squared and adjusted R squared is close to unity, and the VIF is also less than 5. For HTO EFB, this is a result from the surrogate model development, and this is the final form of the heat duty equation, which also consists of the R and T variables. The R squared and the adjusted R squared is also close to unity, and the VIF is also less than 5. For the process analysis for the heat duty from EFB barrel oil, these two equations shows that R has a negative coefficient, and this is valid because heat of cracking required is lesser when the barrel oil blend increases compared to the pure VGO. Next is the T variable. It has a positive coefficient, and this is also valid as higher operating temperature require higher heat of duty. Moving on next is the process correlation for the process heat duty from PKS barrel oil. Firstly, we have the FPO PKS, and this is a result obtained from the surrogate model development, and this is the final form of the equation, which consists of R and T variables. The R squared adjusted R squared is close to unity, and the VIF is less than 5. And here is the H2O PKS barrel oil, and this is a result from the surrogate model development, and this is the final form of equation, which also consists of variable R and T, and the R squared adjusted R squared value is also close to unity, and the VIF is also less than 5. Now let's look at the process analysis for these two equations. Here the FPO PKS has a positive coefficient of R, and it is valid because FPO barrel oil requires slightly higher duty compared to the pure VGO. R for the H2O PKS, on the other hand, has a negative coefficient, meaning that higher barrel oil blend results in lower heat duty. And for T, it has a positive coefficient, and it is valid since higher operating temperature means higher heat of duty. Now let's continue to the second part of the result in discussion, which is surrogate model development for the HP unit. So first, let's look at the process correlation of naphtha yield from EFB barrel oil. here we have FPO-EFP, and this is a result from surrogate model development, and this is the final form of my equation, which consists of variable r and t. The r-squared and adjusted r-squared is close to unity, and the VIF is less than 5. Next, here we have H2O-EFP, and this is a result from surrogate model development, and this is the final form of my equation, which consists of variable r and t as well. The r-squared and adjusted r-squared is also close to unity, and the VIF is also less than 5. So looking into the process analysis for these two equations, it can be seen that R has a negative coefficient, and this is valid since higher bulk oil blend results in lower naphtha yield, while lower bulk oil blend results in similar naphtha yield as pure VGO. For the T variable, it has a positive coefficient, meaning that the naphtha yield increases at higher temperature since hydrocracking reaction flavors at high temperature. Moving on, next is the process correlation of naphtha yield from the PKS bulk oil. Here we have FPO-PKS, and this is a result obtained from surrogate model development, and this is the final form of my equation, which consists of variable r and t. The r-squared adjusted r-squared is close to unity, and the VIF is less than 5. And here is H2O-PKS, and this is a result from surrogate model development, and this is the final form of equation, which also consists of r and t. And the r-squared adjusted r-squared is also close to unity, and the VIF is also less than 5. And here is the process analysis. Based on these two equations, R has a negative coefficient similar to EFP bulk oil, and this is valid since higher bulk oil blend results in lower naphtha yield, while lower bulk oil blend results in similar naphtha yield as pure LBGO. For the T variable, it has positive coefficient, meaning that naphtha yield increases at higher temperature since hydrocracking reaction favor at higher temperature. Moving on, next, here I present to you the process correlation of distillate yield from EFP bulk oil. Here is FPO-EFP, and this is a result obtained from surrogate model development, and this is the final form of my equation, which consists of variable r and t. The r-squared adjusted r-squared is close to unity, and the VIF is less than 5. And here is the H2O-EFP, and this is a result from the surrogate model development, and this is the final form of my equation, which also consists of variable r and t. The r-squared adjusted r-squared is close to unity, and the VIF is less than 5. Looking into the process analysis, R has a negative coefficient, and it is valid since higher bulk oil blend is not variable in producing higher distillate yield. While for T variable, it has negative coefficient, and it is valid because distillate yield decreases at higher bulk oil blend and opposite trend compared to the naphtha yield. Next is the process correlation of the distillate yield from the PKS bulk oil. Here is FPO-PKS, and this is a surrogate model development results, and this is the final form of my equation, which consists of R and T variables. The r-squared adjusted r-squared is close to unity, and the VIF is less than 5. And for this H2O-PKS, this is a result from the surrogate model development, and this is the final form of equation, which also consists of variables r and t. The r-squared adjusted r-squared is close to unity, and the VIF is also less than 5. As for the process analysis, based on these two equations, R for FPO-PKS has a positive coefficient, and it is valid, meaning that higher FPO bulk oil blend result in higher distillate yield, and an opposite trend is observed for the H2O-PKS, which has a negative coefficient. Therefore, it can be said that PKS is a better bulk oil to be blended for a higher distillate yield. As for the T variable, it has a negative coefficient since distillate yield decreases at higher temperature and opposite trend compared to the naphtha yield. Moving on, next I present to you the process correlation of process heat duty from the EFP bulk oil. Here we have FPO-EFP, and this is a result obtained from surrogate model development, and this is a final form of equation, which consists of variable r and t. The r-squared adjusted r-squared is close to unity, and the VIF is less than 5. And for H2O-EFP, here is a result obtained from surrogate model development, and this is a final form of equation, which also consists of variable r and t. The r-squared and adjusted r-squared is close to unity, and the VIF is also less than 5. For the process analysis, R has a negative coefficient, meaning that higher bulk oil blend require lesser heat duty. However, in general, all the bulk oil blends result in similar heat duty. For the T variable, it has a positive coefficient, and it is valid since more heat is required at higher operating temperature. Next is the process correlation of process heat duty from the PKS bulk oil. Here we have FPO-PKS, and this is a result I obtained from surrogate model development, and this is the final form of my equation, which consists of variable r and t. The r-squared adjusted r-squared is close to unity, and the VIF is less than 5. And for H2O-PKS, here is the result from the surrogate model development, and this is the final form of my equation, which also consists of r and t variables. The r-squared and adjusted r-squared is close to unity, and the VIF is also less than 5. In terms of process analysis, based on these two equations, R for FPO-PKS has a positive coefficient, but H2O-PKS has a negative R. However, in general, it can be said that all bulk oil blends result in similar heat duty required. As for T variable, it is positive and it is valid since higher operating temperature means more heat is required. Now we have come to the final part of the result and discussion, which is the GAMS optimization model. And again, here is the integration structure representation. Now let's look at the model formulation. Here I start with the objective function, which is to maximize the profit. The profit equation made up of total sales and also total cost. And total cost includes the raw material cost and also the utility cost. Now let's look at total sales equation first. Here the x8, x10, x9, x11 are the yield equation which can be obtained from the surrogate model development. And this is the cost constant used for these equations. Now let's look at the utility cost equations. The Q here is the heat duty equation, which is also obtained from the surrogate model development, and this is the cost constant used for the heat duty. Moving on next, let's look at the raw material cost equations. The X1, X4, X5 are the supply availability, and this is the cost constant used for the raw material cost, and hence to simplify, this is the final form of the objective function equations. So the objective function equation is subject to the mass balance constraint, the variable constraint, the feedstock supply constraint, and finally the non-negativity constraint. Moving on next, I present to you the GAMS input, and here is the decision variable, and here I declare the types of the variable, and here is the scalar where I declare the cost constant. And moving on next, this is the equation declaration which made up of objective functions, and this is the yield equations, and this is the constraints. And this is also constraint. This is the model and solve statement. And this is a non-linear programming maximizing the profit. And finally, here is the display statement. Moving on next, I'd like to present to you the GAMS optimization result. So by comparing this integrated process with the base case, we can see that the total profit gained by this integrated process is very much higher compared to the base case, which means this integrated process is much more profitable. So in terms of types of bulk oil, FPO-EFB gives the highest profit among all, and the optimum temperature for HP unit is 370 degrees C and 505 degrees C for FCC unit. The bulk oil ratio for FCC unit is around 28%, and for HP unit it's 10%. And now I'd like to talk about the sensitivity analysis. And here I present to you the spider plot for all of the bulk oil. So for this spider plot, it can be said that the steeper the slope of the curve, the more sensitive the profit is to the factor. And based on this spider plot, it can be said that profit is highly sensitive to the naphtha price and also the operating temperature. But even lower operating temperature result in higher profit. Core process should not be operated at such operating temperature. This is because based on the GAMS results, FCC unit should be operated at 505 degrees C, HP unit should be operated at 370 degrees C, and the bulk oil ratio should be from 0 to 20%. So here we have come to the end of my presentation. In conclusion, it can be said that co-processing with bulk oil is a promising and profitable technology. And based on the GAMS result, co-process of crude oil feed with FPO-EFB bulk oil is the most profitable one. And the optimum operating temperature for FCC unit is 505 degrees C and HP unit is 370 degrees C. And for the optimum bulk oil ratio, FCC unit is 20% and HP unit is 10%. And based on the sensitivity analysis, the profit is said to be highly sensitive to the naphtha price. Before I end my presentation, I would like to recommend to conduct an experimental research in order to further validate the simulation result to have a better understanding regarding the dynamic of the model. And that's all from me. Thank you.